Look at this high-resolution scanning electron micrograph showing the composition of human blood. We see red blood cells, purple white cells, and yellow platelets. Every day, the body produces billions of these distinct, highly specialized cells. Despite their different shapes and functions, every single cell originates from a single source, the hematopoietic stem cell, located deep within the bone marrow. These stem cells require a highly specific cellular environment to survive, known as a niche. This 3D cross-section illustrates the marrow's architecture, separating the endosteal niche, lined with bone-forming osteoblasts, and the vascular niche, lined with endothelial cells along the blood vessels. Within these niches, most stem cells remain dormant. They are physically anchored to an extracellular matrix, held in place by chemical tethers, while waiting for specific growth factors to signal them into action. When that signal arrives, the stem cell performs its core biological function, asymmetrical cell division. It splits in two. One daughter cell self-renews, remaining an anchored stem cell to maintain the marrow's reserve. The other detaches and commits to a path of differentiation, morphing into a specialized blood cell. Blood is the product of a continuously regenerating microscopic factory. Because this entire circulatory system depends on precise localized division, the body is acutely vulnerable to system-wide failure if those root stem cells become corrupted. The scale of this factory relies on extreme biological amplification. This tree maps the output of a single hematopoietic stem cell across roughly 20 divisions. Over the course of those divisions, the single origin point multiplies exponentially. The math results in over 1 million mature blood cells generated from that one initial stem cell. If a genetic mutation corrupts a stem cell, whether it is a malignant mutation driving leukemia or a genetic defect causing thalassemia, that error replicates at the exact same exponential rate. The corrupted stem cell continuously floods the body with defective cells. Because the error originates at the self-renewing root level, pharmacological symptom management fails. To survive, the patient requires a complete demolition and total replacement of their entire hematopoietic system. Clinicians must source a replacement system from a healthy donor, but peripheral blood naturally contains very few hematopoietic stem cells. They are locked away inside the donor's marrow. To access them, doctors orchestrate a pharmacological eviction. They inject the donor with a synthetic growth factor called G-CSF, stimulating the marrow to rapidly overproduce stem cells. Next, clinicians administer Plerixafor, a molecular wedge. It directly blocks the CXCR4 receptor on the stem cell, severing its bond with the SDF1 chemokine in the marrow matrix. The anchor breaks, releasing the stem cells into the bloodstream. Over the next several days, the donor's blood is cycled through an apheresis machine, filtering out and collecting the mobilized stem cells. While the donor cells are harvested, the patient must undergo myeloablative conditioning to prepare their body for the incoming cells. Clinicians administer near-lethal doses of multi-drug chemotherapy, frequently combined with total body irradiation. Look at this histology micrograph revealing the physical environment of the marrow post-conditioning. The architecture is hollowed out, leaving large empty fat voids where the dense clusters of healthy and malignant cells have been eradicated. This conditioning is the prerequisite for engraftment. It induces severe immunosuppression to prevent rejection, while simultaneously clearing the marrow niches to create space for the incoming donor cells. This chart tracks the patient's blood cell counts following conditioning. The levels plunge drastically into what clinicians call the Pancytopenic valley, a flat zero line lasting 1 to 3 weeks, where the patient has zero immune defense and zero capacity to generate blood. Surviving this void requires intensive life support. The patient relies entirely on continuous transfusions of red cells and platelets, alongside broad-spectrum antibiotics to fight off microscopic pathogens. At the lowest point of this valley, harvested donor stem cells are infused into the patient's bloodstream. The donor stem cells autonomously navigate the foreign circulatory system in a process called homing. They tumble through rushing blood, detect chemical gradients pulling them toward the vascular wall, and physically squeeze through the endothelium to locate ablated marrow niches. Once engraftment begins, recovery follows a strict biological sequence. Monocytes and neutrophils appear first, to restore basic defenses, followed by platelets. Finally, over the next several months, a completely new T-cell immune system is rebuilt. The success of the entire procedure hinges entirely on the biological autonomy of the stem cell to find its niche without direct human guidance. In an allogeneic transplant using donor cells, the patient inherits an entirely new foreign immune system. The patient's antigen-specific immunity and blood type actually change to match the donor's. This transfer carries a life-threatening risk. The new donor T cells can recognize the patient's healthy organs, like the skin, liver, and gut, as foreign and attack them, a condition known as graft-versus-host disease. This creates a clinical paradox. This exact same aggressive immune response is the mechanism that cures the patient. This is the graft-versus-leukemia effect. Those same foreign donor T cells actively hunt down and eradicate any residual host cancer cells that survived the conditioning chemotherapy. The allogeneic transplant replaces one lethal disease with a new biological conflict. Survival depends on the donor immune system being aggressive enough to eradicate the cancer, but restrained enough to spare the patient's healthy tissues. Modern hematology is moving past the era of total system replacement. The focus has shifted towards targeted, microscopic engineering at the cellular level. CAR T-cell therapy offers an alternative that bypasses the risk of graft-versus-host disease entirely. Clinicians harvest the patient's own autologous T-cells instead of relying on a donor. Using a retroviral vector, scientists insert new genetic code into the host T-cell. This forces a new, uniquely shaped chimeric receptor to sprout on its surface, programming the cell with the precise antigen-seeking specificity of a monoclonal antibody. Unlike the broad, unpredictable sweep of the graft-versus-leukemia effect, CAR T targets the malignancy with engineered precision. The destruction of cancer cells is so rapid that it creates a unique toxicity profile, often triggering a severe cytokine release syndrome. This precision approach extends to non-malignant genetic disorders like sickle cell anemia and thalassemia, utilizing CRISPR gene editing. The process happens ex vivo. Clinicians harvest the patient's flawed stem cells and use CRISPR-Cas9 to rewrite their DNA directly in a lab. For thalassemia, the specific target is the BCL11A gene. A Cas9 complex cleanly snips the designated BCL11A sequence out of the DNA strand, and the DNA refuses. Knocking out this gene removes the suppression of fetal hemoglobin, permanently correcting the defect. By editing the patient's own DNA and reinfusing it, clinicians achieve the curative reset of a transplant while eliminating the lethal paradox of donor-host rejection. The discovery of the bone marrow niche paved the way for the application of systemic myeloablation and total allogeneic replacement. Allogeneic transplants remain a critical life-saving tool, but their inherent toxicity drives science toward the precise engineering of autologous cells. Yet the success of CAR T and CRISPR therapies still relies entirely on the foundational mechanics of conditioning, stem cell homing, and engraftment discovered decades ago. The mechanics of the stem cell transplant, conditioning, homing, and engraftment established the primary framework for cellular therapy. Refining this systemic reset provided the essential architecture required to move from broad replacement to precision genomic engineering.